Hi, I'm Professor Seth Chandler from the University of Houston Law Center, and today's video is on the topic of regression residuals as well as analysis of variance, often known as ANOVA. The essay in this course for Analytic Methods for Lawyers basically has two purposes. I want you to get into the habit of looking at the residuals from a model, and that's really true whether you're using a statistical model, machine learning, whatever you're doing, you want to really take a look at the residuals. It'll help you see if there are problems with your model. Maybe it's misspecified, maybe you're not using the right noise model. There are a lot of things that can go wrong. And so we're going to look at some tests to determine whether the data fits distribution, a particular distribution. We're also going to take a quick look at something called autocorrelation and the exciting Durbin Watson D statistic. And then we'll turn to ANOVA, understand the R-squared statistic better, and something known as the F-statistic. At the end, I will take a quick look at diagnostics on logistic regression, but that's an optional and considerably more advanced topic. Let's start by seeing what things look like when everything goes well. Fit residuals, as I've mentioned in some of the previous videos, are simply the difference between the predicted value for each data point and the actual value. So let's see what it looks like when our model does well. Let's seed our random number generator here. Let's create some data. It's a uniform distribution on -3 to 3. We'll create 1,000 points. And then we'll create the y value, where the true y value is 3 minus 5 times the x value plus some normally distributed noise. Okay, let's run that. Kernel loads up. We're done. Let's plot our data. All right, I don't think it's going to be too hard to fit a line to this. But let's use linear model fit, where we have our data, our basis functions, our variables. Done. And now let's plot the residuals. So we're going to get the data, the fit residuals, and we're going to then plot the x value of the data and the associated fit residual, and then we'll make a plot of it here. Okay? So what you see is on the x-axis we have the x value for the data, and on the y value we no longer have the y value, we have the residual, the difference between the prediction and the reality. So if we look at this, I don't see much of a pattern. And that's exactly what we want. Most of the residuals are kind of close to 0, but there are ones that scatter out here. I don't really see any difference in the distribution if I sort of take a slice here and a slice here or a slice here. It all looks roughly about the same. And again, that's good. That's suggesting that the residuals are not dependent on the x value. So that's what we want. Let's also make a histogram just of the fit residuals. And with a little, not too much difficulty, it kind of looks like a normal distribution. That is what we want to see if we're doing just a traditional old-fashioned linear regression where we think that the noise is normally distributed, because under those circumstances, the maximum likelihood estimate can be approximated nicely by a ordinary least, or is equal to the ordinary least squares estimate. So there are a couple of ways of figuring out whether something is normally distributed. One is using your eyeballs, and actually your eyeballs are pretty good here. The eyeball method I want to show you is called a quantile plot. It's sometimes called a quantile-quantile plot. It's sometimes called a QQ plot. But regardless of what you call it, it involves the concept of a quantile of a list. Let's just review that. I think I've shown you quantiles of distributions, but I'm not sure I've shown you quantiles of a list. So let's suppose we have a list 2, 1, 4, 3, 8, 7, 9, 5, 7, 11, -2, 5, 0. Okay? So, and now I want to know, if I were to sort these numbers, what value would be, for example, about 30% of the way from the bottom to the top? All right, so it's 2, and maybe we could see that. Let's just actually do a sort of those numbers. And you can see that if I go about 30% of the way, I get to 2. If I said, what's the quantile of this same list at 1? Hopefully you know that that's 11. If I say it's 0.7, it looks like it's probably going to be about 7, and it is. Okay, so that's the idea of a quantile. You've also seen the quantile of a distribution. The quantile of a distribution is basically the inverse CDF function. Remember, the CDF says, if I have a distribution and I pick a number x, what's the probability that a draw from that distribution will be below x? And the inverse question is, for what value of x are 70 or Q% of the draws below that? So what I want to do here is I want to look at basically the quantiles of my residuals and the quantiles of a normal distribution. And if those match, here, let's do it. All right, and you see how the points are almost all exactly the same. They're all on this 45-degree line. That's telling us that the fit residuals sure look like they are normally distributed. And just so we're clear, what would happen if I don't know, I did the fit residuals squared? And you can see we would no longer have any sort of fit. Or what if I took the, I don't know, the sine of the fit residuals? That would be insane, but why not? And you can see that although it looks good in the middle, we start to branch off at the end. So that's what a quantile plot does, and it's kind of a nice, simple way of figuring out if your data matches a distribution. But our eyeballs are not foolproof, and so let's talk about a second method. Here, what we're going to say is we're going to form a null hypothesis. And our null hypothesis is that the fit residuals are distributed according to some normal distribution. Okay? And what I now want to know is, what is the probability you would see the kind of data that you do in the fit residuals if that assumption were true? To do this, we're going to use one of these Wolfram language super functions called the distribution fit test. And it basically says, here's your data. I'll let you select how to do it, and I want you to give me something called the hypothesis test data. So we're going to get one of these objects. Okay? And we can find out what properties are available. And by the way, you see, it's already telling us, the first thing it's going to tell us is our p-value is 0.374. And so what this means is that we could very well see the data that we're seeing if the null hypothesis, which happens to be that the data is normally distributed, were true. So we have not disproven the null hypothesis. Let's see what happens if I square this. And then they're telling me, hey, no way, buddy. This data cannot be coming from a normal distribution. Just for fun, and I'm a little curious, what if I do the sine of it? Yeah, it's also smart enough to detect that if I'm getting data that's kind of wavy, it's not coming from a normal distribution. One of the things we can also get, here are all the properties you can get out of one of these objects. All sorts of crazy things, some of which I have no idea what they are, like the Mardia kurtosis. But one thing I do like is the test conclusion, because that's going to explain what it really did. And it says the null hypothesis that the data is distributed according to the normal distribution, something, something, is not rejected at the 5% level, and it's telling you what statistic, what test it's doing. It's doing the Kramer-von Mises test, which it believes is the strongest possible test that is consistent with the assumptions. So, I just showed you what happens when things go well. Let's see what happens when you have a model that doesn't fit very well. So let's create some data again. And this time the truth is that the real model is quadratic, right? There's an x squared term in there, and it does have some normally distributed noise around it. Okay? we can see what the data looks like. And now you can kind of see the curve. But supposing I'm just too busy to actually look at my data, and so I reflexively do a linear fit here where my only basis functions are 1 and x. And there's no way, really, that 1 and x can capture a curve. It has to produce a line. But that's what I do. So I do it, and I get a result. And let's find the best fitting line. And you know, even before I do all the fancy stuff, maybe you can see things are kind of weird. Like the model is low to the left, and it's low to the right, and it's high a little bit in the middle. But let's try our quantile plot method, and let's see what happens when you have a model that's insufficiently complicated to capture the data. In machine learning terms, the bias is too strong. All right, and this is why, you know, quantile plots are fine. You can see the beginning of this deviation here and this deviation here, but it's kind of like looking at one of those weather charts and trying to say, oh, there's going to be a hurricane. I mean, maybe some people can do it, but I think it's challenging. So let's try our friend, let's actually run this code here. And here you can see I'm showing you the residuals as a function of x. And boy, that doesn't look right. Here's our x value. And I don't think it takes real great eyes to realize that there's some curvature here. There's a pattern. The pattern of the residuals depends on the x value. And that should not be true if we have a properly specified model. And moreover, if we do a histogram, you know, the histogram might not be good enough. It kind of looks normal. I'm not sure I could tell you that's not normal. But if we do a distribution fit test again, we get a p-value of 0.528, and so we don't have enough data here. Our test is not powerful enough to detect the fact that there is something dreadfully wrong with our model. Just for fun, well, we got 1,000 data points. I have to say I'm a little bit surprised. It may be because there's just a lot of noise in this data. What if I turn the noise down? Let's rerun this again. I bet it's going to be smart enough to figure this out now. Oh, that's terrible. All right, so now even our eyeballs can tell, hey, something's not right here. Here's what the fit residuals look like. That is awful. Let's look at a histogram of the fit residuals. That sure doesn't look like a symmetric normal distribution. And if we do if we do our distribution fit test, it's telling us this is not normal. So somewhere between having very little noise, when I made the noise standard deviation 1, and having a fair amount of noise when I had a standard deviation of 4, is where we move from being able to detect the problem to having a problem where the effect is insufficiently small for our test to actually pick it up. Okay. I just showed you what could happen if your model specification was bad. But what if your noise specification is bad? Supposing I think that the fit residuals probably come from a uniform distribution. So let's take our fit residuals and find the best uniform distribution I can that fits it. Okay, there it is. And now I can try to see whether our noise, our fit residuals could be coming from a uniform distribution. And I'll get one of those hypothesis test data objects, and it's saying actually not. So if someone told us that the noise was coming from a uniform distribution, we would say no, it's not. And I haven't proven that it couldn't be coming from some other uniform distribution, but I actually picked the best among all the world of uniform distributions. This code picked the best one, so presumably the result would be even worse if I picked an alternative uniform distribution. Let's look at another issue that we might see, which is heteroskedasticity, where the noise is actually a function of the x value. That is, the bigger x gets in my example, or here the magnitude of x, the greater the amount of noise in the data. Maybe the noise is a fraction of the x value, not just some absolute value. So let's get this heteroskedastic data, and you can kind of see that the noise is getting bigger as the x value gets bigger. Supposing, though, I don't know this, and I do a linear model fit, which is going to assume that the data is homoskedastic, that is, it is unaffected by x. I could then do my eyeball test of the residuals, and I'm experienced enough that if I think I would notice, wait a second here, this is a bow tie. I don't think we should be seeing bow ties. We should be seeing the pattern not be dependent on the x value. And while I can't be certain, this looks fishy. So we could do a distribution fit test, and it would tell us, this data, the odds that this is coming from a normal distribution are not good. So we would have to go back and figure out what's going on with our model. Now, as our data gets noisier, I think this was the point I was making before, less artfully, it becomes harder to detect a misspecification. So for example, supposing I do have a quadratic model, but I have a fair amount of noise in it. So that's a bug. That is now swatted. And let's find the best fit. Okay, let's do our residual plot. It's not good. That looks like there's kind of a bend to it. I can do a histogram. Histogram might or might not spot it. What about our distribution fit test? And it's not quite enough noise. There's a little too much noise for me to know for certain that this is actually a quadratic model. One thing I'd like you to do maybe when you work on this is to play around with this noise level and kind of see how the noise level relates to the p-value of the distribution fit test. Let's talk autocorrelation. So up until now, I generated the random data points independently. That is, the value of y for any given x wasn't related to the values of nearby x values or the y values produced by nearby x values. So I now want to change that, and I now want to create what could be called a random walk, which means I'm going to start at some value, and each successive value is determined by the prior value plus a certain amount plus a random deviation. So there's each new value is the prior value plus a drift plus some noise. Okay? So the way we're going to do this is we're going to use a function called nest list. And nest list basically keeps feeding the output of the prior application of the function back into the function again. So this is saying, look, start at 2, and then take that, add 0.02 and some noise, and then take that result and add 0.02 and some noise, and then take that result and add 0.02 and some noise, and do that 100 times. So I did it. Let's plot that data. Let's fit a line to it. Let's show you the best fit plot along with the data. And maybe you can already see something's funky about this in that we have periods in which the residuals are negative, then we have positive residuals, then we have a lot of negative residuals, then we have positive residuals. If I do a list plot of the residuals, you can see it sort of has this curvy feature. This looks like a pattern to me. Moreover, what if I took each fit residual number and then I rotated the list of fit residuals to the left and I tried to capture the correlation between those two? If we haven't done correlation yet, but maybe no. If there's no correlation, this is going to give me a result of about 0. If they're perfectly correlated, it's going to give me 1. If they're perfectly negatively correlated, it's going to give me -1. And so, yeah, that is not what we expect to see if there is no correlation among the residuals. And one statistic we can use that actually captures this better is called the Durbin Watson D statistic. And this is giving us that value, and generally speaking, a value for below 1.522 is statistically significant at the 0.01 level and shows positive autocorrelation. So if you're looking at the residuals and you're seeing patterns like this, you need to test for autocorrelation, and you need to realize that you may not have independent x values or y values here, that they may depend temporally on each other, and you need to be using a little bit different tools in order to analyze the situation. We've looked at residuals, each residual associated with a point, but now I want to look at statistics of residuals, and I want to focus on 2 items. One is an R-squared statistic, and the other is an F-statistic. We're going to start with a simple linear model, and we'll move to the more complex multivariate case. And in the course of wandering through R-squared and F-statistics, we're going to talk about analysis of variance, or ANOVA. Let's create some noisy data. We're going to have our x values be from -3 to 3, and our y values be a linear function of that with some pretty hefty random noise there, normally distributed. All right, there's our result. We can plot it. We can see that there's some relationship between the x and y values. There's a lot of noise. We can generate a null model. That is, here we're just having no x as the basis function. So we're just going to get this model will output a constant that best fits the data. So we get that. Turns out you have to predict something, predict 2.94. Let's get the fit residuals from this null model and take the sum of the squares. Remember, that's what power total does. We'll call that SST. Now, let's do a better model. Let's actually include the x information. And let's run a linear model fit with that more developed set of basis functions. So now we have an idea that it's 2.5 something minus 5.16x. Now let's get the sum of the squared residuals. So we're down to 99,000. Let's see how much we've managed to reduce the residuals by. 77,000. And so the amount that we've reduced it divided by the original total is equal to our r squared. As I suggested in another video, another way to do this is to say, look, I've gone from SSR, that's what I'm at now. My worst case, if I had nothing, it would be SST, and we want to see where on the 0 to 1 scale that is, and it's the same thing. So you can either think of it as a rescaling operation or do it the way that I showed doing it here. So an r squared of 0.437 is good. It's not great, but that's a decent number. You know, if you're seeing r squareds of 0.8 or something, that's something to write home about, particularly in the social sciences. If you're seeing r squareds of 0.1, your model probably isn't doing a lot. But we can actually check a little more scientifically as to whether your r squared is just sort of luck or whether it actually is reflecting the fact that you've got a model that's being successful at prediction. Now, in an ideal world, what I'd like to do is to compute the distribution of an r squared statistic under a null hypothesis and then see where our r squared lands and maybe compute a one-sided p-value. The problem with that is, particularly in the old days when you had to use tables, was that the distribution of r squared under the null hypothesis can depend on the number of variables and the number of data points. So what we what's helpful to do is to figure out some kind of modification of R squared, which is not dependent on the number of variables and the number of data points. And maybe you could use fewer tables. So we're going to compute something called the F-statistic. And the F-statistic is a ratio of two adjusted variances. The numerator is going to use the SSM. Remember, that is the reduction in variance created by the introduction of variables. And the denominator is going to use the SSR. That is the residuals you got when you used your model. Okay? So both of these, numerator and denominator, use this weird thing called degrees of freedom. So what we're going to do is we're going to take, for the numerator, we're going to take the SSM and divide it by its degrees of freedom, which is the number of variables we use to make the prediction, which is just 1 here. And we'll call that quotient MSM. And for the denominator, we're going to take the SSR and divide it by its associated degree of freedom, which is the number of data points, in our example 1,000, less the number of parameters needed to define our regression line. That's 2. So in this example, our denominator is 998, and we'll call our denominator MSR. And now, all we have to do is divide MSM by MSR and get the F-statistic. Isn't that fun? So let's do it. Okay. First of all, let's figure out how much data we have. We've got 1,000 by 2, and the degrees of freedom of the denominator are the number of independent variables, and we're going to subtract 1 from it. So 2 minus 1 is 1. And so to get the MSM value, we're going to take that SSM, which is that reduction in the residuals, which we defined up here, and we're going to divide that by that degrees of freedom that we just computed. So in this instance, the MSM is equal to the SSM, but that might well not be the case if we had a number of independent variables. Okay. Now, we're going to compute how many parameters we had to estimate in our model. And we know we estimated 2 parameters. We estimated the intercept, and we estimated a coefficient in front of the x term, so that's 2. And so our degrees of freedom are this 1,000, the number of data points, less the number of parameters we used. So that's 998. And to get MSR, we're going to divide the SSR, which was the sum of the squared residuals with our model, by the degrees of freedom. And you remember, this is sort of like what we did when we were computing the t-statistic and the z-statistics for regression, where we were basically normalizing these regression coefficients by the standard error. And conceptually, this isn't that different. So the MSR is the SSR divided by this denominator. And now that we've got our 2 ultimate figures, we can compute the F ratio, which is just MSM divided by MSR. And there we go. So that is our F statistic. It's 776.349. Well, whoop-de-doo. We need a p-value. So what we want to do is figure out what would the distribution of the F statistic be if our data had nothing to do with the X value, if our model was basically worthless. And so it turns out that the F statistic is determined by what distribution? The F ratio distribution. And the F ratio distribution has 2 parameters. And what are those 2 parameters? They're those degrees of freedom thing. There's the 2 and the 998. So here's our F distribution. I'm sorry, it's 1 and 998. And now, we're going to take a one-sided p-value, so we're going to compute the survival function of the F ratio distribution with these degrees of freedom evaluated at the ratio between MSM and MSR, and we get a teeny tiny number. So we can do that, all of that work, or we can just ask Mr. Wolfram if he wouldn't mind producing an ANOVA table. And look at that. This number here exactly matches the p-value here, and you can see how these various sums of squares values match what we computed before. So maybe you'll never have to look at what I just did again, but if you ever want to work from scratch and figure out where are these numbers coming from, how are these things computed, that's the process you need to go through. It has occurred to me while listening to this myself that you could be lost in the forest here for all the trees. So let me see if I can boil down a little bit better what's going on. Any model we use is going to decrease the sum of squared residuals, unless it's an unbelievably terrible model. So the fact that your model reduces the sum of squared residuals may not mean that your model is doing a lot of work. And so what we kind of want to see is what is the likelihood that a random model, a garbage model, would reduce the sum of squared residuals by as much as you managed to reduce it through use of your own model. And that's basically what we're getting at with this F-statistic, and we're able to generate a p-value. So maybe that gives you a little bit of a bigger picture view of what's going on here. That was ANOVA with a univariate linear regression. Let's look at ANOVA with a multivariate linear regression. Here's our data. We're drawing from a uniform distribution with 3 variables. And here is our true model. It's 0.63 plus the dot product of these coefficients and x plus some noise. So let's produce our data. This is what it looks like. Let's run again linear model fit with no x, y, or z in the basis functions. This is our null model. Okay, if you have to guess a number, guess 1.55. Let's get the sum of squared residuals. Now let's run a decent model where we're actually using the x, y, and z information. There we go. Let's get our sum of squared residuals. Let's figure out how much we reduced the sum of squared residuals. We reduced it by 263,000. What's the ratio of the amount that we reduced it divided by the amount that we started with? And it's 0.23. Alternatively, I kind of am thinking I've grown to like this better, where we take the amount of squared residuals under our model, and we scale that the same as, look, this is the worst it could be. This is if we had a perfect model of 0, and we want to go from 0 to 1. And, right, that's because I forgot to use the right variables, and now we get the same thing. So, with our 3 variables and this model, we get an r-squared value that's bigger than 0, but it's not like my 0.4 thing or 0.8. So maybe we got lucky. Let's take a look and do ANOVA again. I'm going to do it by hand again, and then we'll talk some more about what you can do with linear model fit. Okay, let's once again get the dimensions of the data. We've got 1,000 by 4, although really one of those columns is the answer. It's not the covariates that are being used for prediction. So let's figure out basically how many variables we're using for prediction, and we'll divide the amount that we reduced it by this number of variables that we have. Now we have the numerator, 87,000, etc. To get that denominator, let's first of all figure out we've got this many data points to begin with, 1,000, and we're going to subtract off the number of parameters that we're estimating, which is our intercept term, plus the ones in front of the x, y, and z values. Is that what I called them here? Yeah, X, Y, and Z. Okay, great. So that gives us 996, and now we're going to divide the remaining sum of squared residuals by that 996. That's going to give us the degrees of freedom. I'm sorry, that's going to give us our denominator, 877. And now we'll compute an F ratio, which is this 87,000 thing divided by the 877 thing. And we get 100, more or less. And now we can compute the p-value using an F ratio statistic. And the F ratio statistic has these two parameters. Let's actually see what those are going to be. So it's an F ratio statistic of 3 and 996. And let's evaluate it at this F ratio 3 number. And we get 1.26409 times 10 to the negative 56th. And so we would not be seeing data of 0.23 if there were no relationship between the X, Y, and Z values and the thing that we're trying to predict. Or we could get pretty close to this number that we computed here by just taking our linear model fit, the fitted model that emerged from linear model fit, and computing the ANOVA table property. And you can see that there are p-values associated with the X, Y, and Z statistic. Unfortunately, it does not tell us directly the p-value statistic associated with the entire regression. And so what I've done to help you is to write a little function that will automate that process for you going forward. ANOVA model, and there it is. And so you can, it basically gives us most of the information that's here, but it adds in a p-value to let us know whether our model is worthless. I'm going to let you look through this code and see what does happen when you do in fact have a worthless model, and whether what kind of p-values you get under those circumstances. Or I'll let you work it through, but here, let's just do it. And you'll see that when our model is worthless, we do not get a p-value that's less than 0.05. One final point, adjusted R squared. Did you see that when we computed the R squared for our worthless model, we did get a positive number? And so there is another property emerging out of linear model fit called adjusted R squared, which takes account of the fact somewhat that R squared's always going to be positive even when the model is worthless. It's not a great adjustment factor, but it's something, and we should get an even smaller number. So sometimes you'll see people talking about adjusted R squareds, and they should be using an adjusted R squared in general to take account of the fact that any regression you do, even if you have a lousy model, it's going to give you some positive R squared. So this concludes the compulsory part of the video. There is this optional part that follows on Pearson residuals and logistic regression. So in the first part of the video, I showed you how you could diagnose specification errors or potentially autocorrelation by taking a look at the residuals. This becomes more challenging with logistic regression, and in fact, exactly how to do it is still an open research area. But let me see if I can explain why you can't just look at fit residuals with logistic regression quite the same as you did with linear regression. The fit residuals for logistic regression should never be normally distributed. Let me see if I can give you my proof. Okay, the fit residual for logistic distribution can never have an absolute value greater than 1, because the real values are between 0 and 1, and your prediction is between 0 and 1, so the difference can never be bigger than 1. But normal distributions definitely take on values whose absolute value is greater than 1. QED. All right. But maybe we can patch things up. Supposing we divide the fit residual by the standard deviation of the Bernoulli distribution at the predicted response value. That is, Bernoulli distributions have a standard deviation. Let's just write it out here. Bernoulli distribution of P. That's our formula. We can plot it. Let's just plot it from, as P goes from 0 to 1. And it, I don't know, looks like a semicircle to me. But the big point is that it's big in the middle and very small at the extreme values. So if we divide, and our residuals are likely to be small at those extreme values. So if we divide our residuals by the standard deviation of the Bernoulli distribution evaluated at the predicted point, we maybe would get something that looked a little more normal. And in fact, there are some internet sites that incorrectly say that it will be normal. That's not exactly true. But let's do an experiment here. All right, let's take some data. Let's draw some x values from -2 to 2. We'll draw 1,000 of them. And here's our true function, 0.3 minus 1.2x. And so we will produce our x, y values. Now we'll do a logit model fit on it using our basis functions of 1 and x. You do need to have seen the logit model fit video or read the materials before you're going to follow this at all. All right, we're done. And now let's get a histogram of the Pearson residuals, not the fit residuals, not the deviance residuals, not the null residuals, not the Anscombe residuals, the Pearson residuals. All right, and there they are. So it sort of looks symmetric, and it sort of looks like if we could just fill in this little thing, it would be normally distributed. So I'm going to say it's normal-ish, and I have done a lot of literature searching, and I can't find anyone who accurately tells me what this distribution is, but at least it's sort of normal-ish. What if, however, my real data is not a linear function of x, but it's a quadratic of x? So here's my nasty data, but I don't know that that's how the data was generated, so I just go ahead and do a regression with basis functions of 1 and x, and I don't include an x squared term. And now I look at the residuals. And now it's asymmetric between 0. It's a complete mess. And so when you see something that looks like a complete mess like this, I think you need to be asking, I wonder if they misspecified their model. And if you have an expert who's done logistic regression, you should ask them what diagnostics they used to make sure that their model specification was appropriate. And unless you have a good expert, they're going to give you a blank stare, or they're going to say, well, I didn't do any diagnostics. They just assumed the specification was appropriate. And if that's the case, you might try computing some Pearson residuals yourself. And if they look funny, like this, then that expert has probably done something wrong. All right, so this concludes the video on regression residuals.